Welcome to the Hidden Heroes podcast. It's a collection of stories about tech pioneers who, over the past decades, laid the groundwork for the digital revolution. They, in a way, shaped the way we live, work, communicate, or travel. That's why, together with Stephen Johnson, who is the author of all the stories, we are on the mission to bring these pioneers into the spotlight and give them credit they truly deserve. In today's episode, we dive into the story of Radia Perlman, a pioneering computer scientist and network designer. She's contributed more than her fair share to the internet invention over her long career, teaching a whole generation of network designers in her wake. Brought to you by Netguru.
The Magic Box and the Spanning Tree: How Radia Perlman Made the Internet Work, by Stephen Johnson. We take it for granted that decentralized networks like the internet just work. But decades ago, pioneering computer scientist Radia Perlman solved a crucial problem that made those networks possible. If you do not happen to be an expert in computer networking algorithms, the headline description of U.S. patent number 7339900 may seem a little mysterious to you. Quote, method and apparatus for preventing spanning tree loops during traffic overload conditions. The lay reader might be forgiven for thinking it involves some kind of innovation to help city planners route automobile traffic around fallen trees. But in fact, patent number 7339900, one of more than 100 held by pioneering network designer Radia Perlman, is a tool for stabilizing information traffic, not automotive. When you connect your local Ethernet network, your computers and smart TVs and game consoles, to the wider internet, and the information flows reliably between those two networks, that connection is quietly made possible by innovations like those described in patent number 7339900. Our understanding of networks, how to make them stable, self-correcting, efficient, is a remarkably young science, given how much the modern world now relies on the consistent flow of information across them. We tend to focus on the glittery applications that we interact with directly, TikTok and Chrome and Spotify, but all those apps would be worthless without the quiet miracle of stable network architecture, seamlessly connecting servers and routers all around the world. That architecture was the product of many minds, each contributing small pieces to the puzzle that over time has given us the network stability that the entire world depends on. Radia Perlman contributed more than her fair share of those pieces over her long career, and probably did as much as anyone to explain how stable networks worked, teaching a whole generation of network designers in her wake. But if U.S. patent number 7339900 is only part of the story of the network revolution, one of many patented breakthroughs that have long been neglected by the very people who benefit from them, it does stand out from the pack in one crucial respect. It is probably the only software patent on record that features a poem. The fact that Radia Perlman is now a member of the Internet Hall of Fame and is widely considered to be one of the pioneers behind the networking revolution would have likely surprised Perlman herself growing up in suburban New Jersey in the 1960s. Quote, there's this stereotype of engineers that they always took things apart, she says now with a smile. I never took anything apart. It never occurred to me to do that. I would have assumed that I would break it or get electrocuted or something. We sometimes forget that while software became a field dominated by men in the 80s and 90s, now thankfully trending back towards a more gender-diverse mix, many influential early programmers in the 1960s were women, like Grace Hopper, creator of the COBOL programming language. But while Perlman got a taste of programming in her high school years, when a teacher encouraged her to take an outside class on computer science at the Stevens Institute of Technology, the initial encounter was not exactly an encouraging one. Quote, everyone was bragging about how they'd built ham radios when they were 7. I had no idea what a ham radio was, she recalls. And then they were asking questions with fancy words like input. I had no idea what that meant, and so my mind shut down. I got nothing out of that class because I felt I was so many years behind I'd never catch up. If someone had asked me what I was interested in doing, I would have said, oh, anything, as long as it's reasonably interesting and as long as it doesn't involve computers, she adds. When I learned to program a few years later, I realized it was fun and not difficult, but But this experience made me understand the sense of panic that can cause someone perfectly capable of learning something to fail because they believe they cannot do it. Shortly after that unpromising taste of programming at Stevens, Perlman enrolled as an undergrad at MIT, one of only 50 women in a freshman class of roughly 1,000. In an interview with The Atlantic several years ago, Perlman recalled that women were so scarce on the MIT campus that she'd find herself startled when she encountered another woman in her classes. I'd noticed that it looked kind of weird, this other gender person looking curiously out of place in the crowd. I'd have to remind myself that I was also that other gender. While Perlman was majoring in math, her years at MIT gave her another pass at computer science. I was taking a physics class, and the TA said, "I have a project, and I need a programmer. Would you like to be my programmer?" And I said, "I don't know how to program." And he said, "Yes, I know. That's why I'm asking you, because I have no money to pay you." Before long, Perlman had taken a job at nearby BBN Technologies, one of the core organizations responsible for the development of ARPANET, the early predecessor of the Internet. It was at BBN that Perlman found her true calling, exploring the new science of network protocols. Software programs were linear, prescriptive. They worked because they operated in an environment that was utterly predictable, just you and your code in dialogue with a CPU that followed a fixed logic. Network protocols were about something different, the flow of information and the strange eddies and whirls that could form in those networks. A key part of designing the protocols involved building systems that were resilient when confronted with unpredictable behavior. A protocol designed to last for decades has to be flexible enough to interact with computers that haven't even been dreamt of yet, much less manufactured. And it has to be able to adapt to new network architectures that might emerge, new ways of connecting new machines. BBN was really the dawn of networking, Perlman says now. I was designing routing algorithms, and I discovered I loved it. You have all these little things, all doing their own little thing based on local information. And somehow it all fits together, like a beautiful symphony. I can think that way, whereas a lot of people can only think in a linear way. One of Perlman's first published papers identified a crucial vulnerability in the design of ARPANET. Quote, "A few mangled packets could cause the network to go down forever," she explains. "If your PC gets into a bad state, you just reboot it. But you can't reboot a network." In those days, rebooting the ARPANET would have meant calling all the computer science labs around the country connected to ARPANET and asking them individually to turn their routers off and on again in sync with everyone else. This was an unacceptable burden even back in the 1970s, when the total number of nodes on the ARPANET was still relatively small. On today's internet, it would be unthinkable. Diagnosing that vulnerability made it clear to Perlman that what networks required was what she called self-stabilization, the ability to recover from mangled information or bad actors or crashed computers. One of the great underappreciated miracles of modern life is the fact that the internet itself, this massive network of networks connecting billions of devices, is staggeringly reliable. That stability emerged out of thousands of specific design tweaks to the underlying protocols, but it also, more generally, emerged out of the pursuit of scalability and self-stabilization as a principal goal of network architecture. Perlman wanted to make network routing easier to manage, which was important in making networks to be used by real people, not just computer science researchers. The spanning tree algorithm grew out of an industry mistake, thinking that Ethernet was a network rather than a link in a network, Perlman points out. The spanning tree protocol that Perlman designed in the early 1980s is a marvelous case study in network protocol design. It's not a feature that users experience directly, like a cloud-based word processor or a hypertext browser. But without the resilience it creates, our experience of those more obvious features would be seriously impaired. Perlman's first major work after joining Digital Equipment Corporation, DEC, in the early 1980s, was designing routing for DECnet, a protocol that is still widely deployed in the internet today. Her contribution and innovations made networks more robust, easier to manage, and more scalable. But there were still certain limitations. As Perlman explains it, when Ethernet was introduced, the industry made the mistake of thinking that the Ethernet was the network instead of a link in a network. Just as the post office depended on people putting a letter into an envelope saying where it's supposed to go, routers depend on computers that transmit data, adding information that the routers can read. When people built applications assuming the entire network was a single Ethernet, routers were not able to forward data from one Ethernet to another. The basic concept of a bridge was to listen to all the transmitted packets and forward them onto the bridge's other ports. But that would be a disaster if there were loops. The solution was the spanning tree protocol. A network is a kind of relay race, with packets of information passed along instead of batons. A computer sends a packet of information out onto the network with an ultimate destination attached to it, and it is relayed from one node to another along the network until it reaches its final destination. Imagine a city mail system where individual letters are passed along from mailbox to mailbox, slowly making their way towards the recipient's address. Mailbox number 1 doesn't know how to get the message all the way to the final destination, but it does know how to send it to mailbox number 2, which is closer to the recipient's address. And mailbox number 2 knows enough to send it to mailbox number 3. Now, the problem with a system like this is that every now and then loops appear in the network. And while the message won't be circulating in the network forever, it might not reach the destination as the looping packet will be discarded after a certain number of forwards. Now, without getting into the technical details, existing routers could not forward packets between links unless the end nodes added extra information to the data. Building a bridge, which would forward information based on end nodes acting as though they were attached only to a single link, requires a topology without any loops. One day, my manager came to me and said, "Radia, we need to design a magic box that sits between two Ethernets and lets someone on this one talk to someone on that one," Perlman recalls. Something that she'd been designing for years now involved an extra challenge. Quote, "To make it so there were no rules on how you plugged it together, you could have a bunch of drunk monkeys with Tinker Toys, and it would still work with zero configuration." The magic box had to prevent loops from occurring, and it had to adapt seamlessly to changes in the network architecture. Quote, "And then he thought he was being witty, and so he said to me, 'Oh, as long as I'm giving you this impossible problem, to make it more challenging, the amount of memory necessary to run it should be constant, no matter how many links and bridges there are in the world.'" Now, he mentioned this on a Friday, and he was on vacation the following week. This was before email and cell phones, so he was going to be absolutely unreachable, she says. It seemed initially to be a daunting task, perhaps an impossible one, but it was also exactly the sort of problem that Radia Perlman had been wrestling with since those early days at BBN, how to make networks self-stabilize in unpredictable conditions. So that night, I realized, oh, wait a minute, it's trivial. I know just how to do it. I can prove it works, she recalls. The key insight behind the solution came from a metaphor of sorts, imagining the network not as a series of mailboxes or superhighways, but instead as a tree. Even though she describes spanning tree bridging as a kludge to rescue the industry from a mistake, it is very widely deployed today. The original shared linked Ethernet could only support a few hundred nodes. Spanning tree bridging has replaced the original shared link concept of Ethernet, and what people now know of as Ethernet today can support very large networks. Perlman wrote out the spec for the spanning tree protocol in a matter of days. It has an elegant simplicity to it. The goal was to create a loop-free subset of the network, a tree, that reaches all the links, a spanning tree. The protocol works by having one bridge choose to form the root of the tree, and then it employs a mathematical formula to determine the shortest paths from that root. In her tree metaphor, it is as though each leaf at the end of each branch has a single line of connection that stretches back down to the tree's roots. None of the leaves needed to know the complete graph, or even how big the network is. Once the tree has been computed, each bridge forwards traffic from any port selected to be in the tree to all the other ports selected to be in the tree, ensuring they don't get lost in a loop along the way. It was such a simple algorithm that I wrote the spec and it was complete by the end of the day on Tuesday, Perlman says now. And it was so complete that the implementers got it working in just a few weeks without asking me a single question. But this was Tuesday and my manager wasn't around and I had to show up and I couldn't concentrate on anything else. So the remainder of the week, I worked on the poem that goes along with the algorithm. The simplicity of the spanning tree protocol initially masked its own power and led some of her colleagues to underestimate her skills as a protocol designer. My designs were so deceptively simple that it was easy for people to assume I had just easy problems, Perlman said in a 2014 interview. Whereas others who made super complicated designs that were technically unsound and were able to talk about them in ways nobody understood, they were considered geniuses. In 1985, she published a description of the approach in a paper entitled An Algorithm for Distributed Computation of a Spanning Tree in an Extended LAN. Over time, the industry came around to Perlman's spanning tree. DEC incorporated it into the Internet Bridge it began selling in the mid-'80s, and it became a part of the industry standard IEEE 8021D in 1990. Before long, an idea that had seemed obscure or irrelevant to most people, getting one computer network to talk to another, would become an essential component of everyday life around the world. Perlman's self-stabilizing protocol helped make that unlikely revolution possible. In 1992, Perlman published a textbook on network protocol design, Interconnections, that quickly became a classic in the burgeoning science of network theory. Though her designs had played a significant role in advancing the cause of self-stabilizing networks, it was the textbook that made her a household name in the field. After Interconnections came out, she recalls, I'd meet people at conferences and they'd look at my name tag and say, "Oh, you're the Radia Perlman who wrote Interconnections." As with her network designs themselves, Perlman's writing had a clarity that made it an invaluable resource in computer science programs. She took complex ideas and made them intelligible. Quote, "There is considerable confusion in this area," Perlman wrote in the introduction to the second edition. "Most of the terminology is ill-defined and is used in conflicting ways. The terminology and the specifications tend to be daunting. Some knowledge is spread among many different documents. Much is unwritten folk wisdom. Adding to the confusion is dogma. Beliefs are accepted as truth, and questioning of any of the dogma is often greeted with hostility. But good engineering demands that we understand what we're doing and why, keep an open mind, and learn from experience." 30 years after Perlman had been repelled by the insider jargon in that programming class at the Stevens Institute, she had become a master explainer herself. Perlman continued to modify and improve her protocol designs in the years to come. In 2003, she was granted a patent for one of those improvements, a modification to the original spanning tree solution that helped network bridges better manage the information congestion that could occur during periods with unusually high amounts of traffic. It had been many years since her manager at DEC had challenged her to invent a magic box, but in filing the patent, her mind went back to that eventful week, and she decided to include a memento of sorts in the background description of the invention, included in the patent application, the poem she had composed in the restless days waiting for her manager to return from vacation. Perlman had been designing algorithms as her day job, and so she gave the poem a fitting name, Algorhyme. "I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity. A tree that must be sure to span so packets can reach every LAN. First, the route must be selected. By ID, it is elected. Least cost paths from the route are traced. In the tree, these paths are placed. A mesh is made by folks like me. Then bridges find a spanning tree."
Thank you so much for listening. If you enjoyed this episode, subscribe to our podcast so you won't miss the next Hidden Hero story. And to learn more about the Hidden Heroes Publishing Initiative by Netguru, visit hiddenheroes.netguru.com. Until the next time.